Hello, everyone. So this lecture is about experimental methods for hypersonic flows, and I'll mainly be talking about how you can simulate hypersonic flows using methods like wind tunnels or shock tubes. So I know most of you guys already have an idea of what a wind tunnel is and how it performs, but in the next two slides, I'll kind of cover some of the basics of wind tunnels as a whole, just to kind of maybe keep it fresh in your mind. Now, to start off, wind tunnels are just large tunnel-shaped devices that push flow over objects. And usually these objects are scaled down to some size, maybe around 1/10 or 1/30th of the full-scale body. However, there have been some experiments conducted on smaller planes, like the full-size plane, but this is kind of rare, and usually you do have a smaller model of it. Now, scaling down these models kind of it provides us a cheaper mock-up of the full-size body. So it kind of makes it relatively cheaper than actually physically testing this, especially in the case of like something like aerospace industry, where you have very large vehicles. You can't simply just physically test this, in space or something like that. I also want to emphasize relatively cheaper, just because hypersonic wind tunnels can be very expensive compared to, say, subsonic wind tunnels. Now, in order to scale these models properly, we use the non-dimensionless Reynolds number, and this kind of allows us to simulate various fluid properties. So using Reynolds number as a scaling factor kind of breaks down when going to compressible flow, and that's kind of why in transonic and supersonic wind tunnels, you generally match your Mach number instead of your Reynolds number, such as in the case of the subsonic region. Now, there are some cases where you generally want to match both your Reynolds and your Mach number, but this requires special pressurized or sometimes cryogenic wind tunnels instead. And then I also like to point out that you can perform dynamic studies as well, such as maybe a rotating or moving body, but you might need to have some dynamic scaling involved as well, such as scaling properties like moment of inertia, your center of mass, or even sometimes, depending on the experiment, you might want to scale your material properties. So some of the potential issues, especially with wind tunnels, are power and cost, like I mentioned before. And this is more so seen in hypersonic speeds, since it does require a lot more power to push this fluid. Now, since there is also this increase in power requirement, then you're also going to tend to see shorter simulation times. So in the case of some hypersonic wind tunnels, you'll see simulation times of about 1 second. So this can kind of be very short. Now, also blockage factor is one of the next big potential issues that you can encounter even in subsonic wind tunnels, not just hypersonic ones. But this factor is essentially just the ratio of the frontal area of the body to the cross-sectional area of the tunnel. So if you can imagine this dash box around this plane, like in this diagram, this blockage factor is very high in this picture. Now, a typical blockage factor that you would probably want is around maybe 3 to 5%. So generally, you want a lot more room on all sides. You can see that this tip of this airplane is very close to this wall. Now, this becomes very important when you start to look at aerodynamic effects such as wingtip vortices or maybe even shocks. So in this specific diagram, there is a wingtip vortex coming off of this plane on both sides. And since the wall is very, very close to it, the vortex doesn't have very much room to dissipate. So it's running into the wall, running back into the wake of the plane, and it can interfere with the flow. And this causes poor results, and it doesn't actually really simulate what you would actually see in free stream flow. Now, this same idea can be applied to shocks as well. So imagine if you had a shock on the leading edge of this plane. It can reflect across your test section, which can change your results. Also, one last thing I would point out is that all these kind of go hand in hand because, in order to increase your blockage factor, you have to increase this area, this test section area. And by increasing this test section area, you're also increasing this power requirement, which generally would probably reduce your simulation time as well. So now moving on to hypersonic wind tunnels. I kind of like to revisit the power that I keep talking about. So to kind of give you an idea of how much power we're talking about, just imagine doubling your cross-sectional area or maybe even doubling your flow density. And then this results in doubling your power. But in the case of, hypersonic wind tunnels, you might see, say if you want to double your velocity or, double your Mach number, this would effectively quadruple the power required. So you're no longer, it's no longer linear. It's increasing with the square velocity. This can be, you can see this as an issue moving to faster flows like Mach 20. It's going to be a lot more difficult to approach this. So now there's a lot of different configurations for hypersonic wind tunnels, but the most common would probably be the blowdown wind tunnel design, which is shown in the bottom right over here. So now I'll go ahead and blow that view up. So you can probably tell right away that this is slightly different from a subsonic wind tunnel. One of the biggest differences is that subsonic wind tunnels tend to have a turbine to move the flow, and they have less aggressive converging and diverging nozzles. And the reason why this kind of doesn't really work is because in subsonic flows, it's incompressible flow, but as you move to supersonic or maybe even transonic flows, you reach a incompressible state. Compressible state, and then this way your turbine is kind of less effective because it's only really designed to move a lot of mass and add a little bit of velocity to it. So in this picture right here, it's actually pressure driven. So there's a pressure differential between the left side and the right side. So this left side has a very high pressure vessel, while the right side has a low pressure vacuum. You can also notice that on this left side, you also have a heater, or sometimes called a dryer, and then you also have a pump or multi-stage compressor. So this dryer, effectively, it helps reach the stagnation temperature within the test section, and then this pump helps reach the stagnation pressure in this section. This dryer also has multiple functions. It's not just to reach the stagnation temperature, although that is kind of like one of the primary concerns, but it can also help remove any potential moisture. Another thing that I like to talk about is that as you expand this throat right here, the temperature drops very quickly. And that's kind of like one of the reactions of talking about supersonic flows. So essentially in Bernoulli's, you're used to increasing cross-sectional area reduces the velocity. But in supersonic flows, you kind of see the opposite. So, and this is kind of caused by the temperature and the pressure and the density building up right here. So as you expand this, this temperature, density, and pressure, it's all reducing very quickly. And so this can kind of have some negative side effects, like the air can actually liquefy. And, obviously that won't be very accurate for the simulation. And so at least in the case of air, this happens around maybe Mach 4 or Mach 5. But this heater right here, or dryer, it can help keep this air above the liquefaction point. But this issue arises even further whenever you're talking about like Mach 20, because at higher speeds, it becomes very difficult to reach this increased temperature to keep the air from liquefying. So you can imagine just say at lower Mach numbers, you have to increase the air by maybe a little bit amount of temperature, but as you increase, faster and faster and faster, you're going to have to increase this temperature more and more and more. Now, one of the ways to get around this is that some wind tunnels use helium or nitrogen, or really any other gas that has a lower boiling point. Next, the valves. So these valves are located on both sides. Now, once the valves are opened, obviously the high pressure fluid rushes to the vacuum sides until both sides reach an equilibrium. Then this test is essentially complete. And then the throat right here, I'll talk about both the throats and the test section right here. So as the fluid reaches Mach 1 in the first throat, the cross-sectional area, like I said, increases to allow the built-up pressure and temperature and all that stuff to help the fluid reach the test Mach number. There's actually a great YouTube video about this process for like a Mach 20 wind tunnel where he explains this process very well and he kind of goes into more detail about everything. And I'll probably link that video to the description of this video if you guys want to watch it. I thought it was very interesting. It showed a lot of cool diagrams and stuff. But the second throat over here, it just slows the flow back down to subsonic speeds. And that's essentially this blowdown wind tunnel design. Now, some advantages to this design are that it can achieve relatively high Mach numbers pretty easily just because it's driven by a pressure difference. And it's also very easy to design and has a very quick start time to reach this hypersonic flow. However, maybe some of the drawbacks that you might see are very short test times, like I said before, which causes, more expensive instruments to use. And also one more thing is that it can be very, very loud. So next up is shock tubes or shock tunnels. Now, these behave very similar to blowdown wind tunnels in which they are pressure driven, but there are some differences. A shock tube is essentially just a closed tube on both sides, and the purpose is to help simulate shocks, or sometimes they're even used for combustion. So the left side is the driver section, and the right side is the driven section. Now, this left side is compressed with a piston, which essentially causes this gas to increase in pressure. And then at a certain point, there's this diaphragm right here that ruptures. And this causes, all the fluid, all this compressed fluid from the left side to rapidly go to the right-hand side, just because of this pressure differential. So this can kind of lead to hypersonic flows. And, the importance of this is just, and it's a very easy way to kind of simulate shocks and, look at just different combustion reactions. So next, I'll kind of talk about how to collect the data. So this top equation right here is used to measure the stagnation pressure, and this is usually measured with a pitot tube. So it just takes a pressure and all that. So this specific equation can provide the your free stream Mach number, and then from this Mach number, you can then go to you can find the static temperature down here using this equation. So you can plug in your free stream Mach number, and you can get back your static temperature in the test section. Now, once you know all these parameters, you essentially can pretty much calculate any fluid property you want. You can, you can, test for your density, your temperature, velocity, any of that stuff. You basically have all that. Finally, these forces and measurements are taken with a variety of sensors or other tools such as a pitot tube. You have pressure sensors, thin film sensors, thermocouples, everything like that. And like I said, with hypersonic flows, you're moving at much faster velocities. So you're going to need, better equipment in order to handle this very rapid change in difference between subsonic and hypersonic. And then from this, from all these sensors, everything, you can use these equations and you can, like I said, backtrack all to get any fluid property. So essentially that's it for the experimental methods lecture that I have for today. Thank you.